Okay, welcome. We got another problem, similar problem as the last video I just posted, an infinite wire that goes from negative infinity to infinity, and we want to find the magnetic field at this point P, magnetic field, a distance D from the wire. Last time we showed everyone how to do that with the Biot-Savart law. Now we have a different law. Use Ampere's law to find the magnitude of the magnetic field at a point P that is a distance D away from the infinitely long wire carrying a current I. Express your answer in terms of variables given and physical constants. In the Biot-Savart law, we saw that B wire is equal to mu naught I over 2 pi D. So we are doing exactly the same problem, except in this case, we are using Ampere's law. Two different laws. The Biot-Savart law led to that. Ampere's law is doing the same thing. So it should lead to the same answer, right? It's just two theories leading to the same answer because the setup is exactly the same. If you have two theories explaining the same physical phenomena, but they lead to a different answer, something's wrong with one of the theories because physics is not just going to change depending on how you describe it. It's going to be the same thing over and over unless something changes with the experiment. But in this case, we have exactly the same setup. So I'm going to start the same way and just Google search or ask my friend chat, what is the Ampere's law? Let's peep. And again, this is why I really like studying with equation sheets, because if you can explain an equation and each little property inside of it and you know how to use it, then you're kind of like really chilling. So this is a different looking equation. Ampere's law, Ampere's law is right here. We have an integral with a circle in it. We have b dot d, is it ds? I'm not sure. I'm going to check. I know here that there's mu naught and this I has an enclosed in it. Mu naught I enclosed, this is dl. So this is very similar to Gauss's law. Check my Gauss law video. You have a very similar equation to this. I think I also did an Ampere's law where I kind of explain what's happening here. So I'm going to just zoom through it very quick. This little circle is an Amperian loop. It is a two-dimensional object defined by a one-dimensional edge. This is the one-dimensional edge, dl. So if I have the wire here and I turn it to face you guys, I basically have a wire like this that goes on forever. I take a cross section and the current here is going this way. So if I take the wire, face it like this, the current is coming like this out of the page. So this is the current out of the page defined by this dot. I can draw a Amperian loop, two-dimensional object like this around the wire. Over here, it would look kind of like a little hula hoop going like this. I want to set up the problem such that my Amperian loop is just big enough so that the edge over here touches the point P where I want to calculate my magnetic field. So let's say the point P is here. That means the Amperian loop has a distance d, right? Because I grow the Amperian loop such that its radius is the same as this distance. So I can calculate the magnetic field here. Same kind of thing with Gauss's law. Now that we have this set up, this dl is actually a vector. So is b, vector, vector, dot product between two vectors. So we know that b here is going a specific direction. How can we calculate that? The right hand rule also helps. This is my right hand. My thumb can now point in the direction of the current, and these fingers wrap around in the direction of the magnetic field. So if my thumb is pointing here, my fingers curl into the page here, into the page. Same thing with when we did the Biot-Savart law, except they didn't ask us for the magnitude, or sorry, they didn't ask us for the direction of the field, but it is important to know. So in this case, the current is going this way. That means the magnetic field is circulating around this way. So thumb in the direction of current, fingers wrap around in the direction of the B field. B field is going this way. The reason this is important is because this dot product cares about directionality. This dl, now we're going to define it. I just said that this Amperian loop is a two-dimensional object defined by a one-dimensional edge. This is the one-dimensional edge. Boom. Just the boundary of the circle. This is the one-dimensional edge. So at each point in this edge, we want to create a little dl. with directionality. So you can choose this DL to be facing this way, counterclockwise, or this way, clockwise. I am choosing this way because if I go around, there's DLs along each part of this Amperian loop. One here, and they all have to face the same way. So here, at exactly this point, my DL will be facing the exact same direction as B. Because that's the case, the angle between these guys, theta, is equal to 0 degrees. Why am I doing this? Check this out. We're going to use Ampere's law. Write it down over here. Mu naught. This I enclosed is telling you or asking you, what is the current enclosed by my Amperian loop? Since the Amperian loop I chose was here, I, the total current is I. If you shift the loop here, the total current enclosed in this area is 0. There's no current. So that is important to know. It changes with every problem. If I add another wire here, the enclosed current will be different. If I change the direction, so I have two wires facing in opposite directions, their currents going in opposite directions, and I enclose both of them, the enclosed current would be 0 because you add a positive with a negative if the currents are identical. So, that being said, I'm going to erase this so I have some room to work with here. I'm going to go like that. Remember this. So now we can do integral closed loop. This B dot to ds has a very similar way of expanding it, just like the cross product in Ampere's law, except this is the dot product. So how you expand this is magnitude of B times magnitude of dl times cosine of the angle between them equals mu naught I. If this stuff scares you, you have to take a look at some vector videos, cross product, dot product, how to expand those. I did some videos related to that. Check those out if you want a quick kind of refresh guide. Probably not quick, it's like a 40-minute video. Anyway, now we can plug stuff in. This DL has a length of DL. It's super thin, we don't know its length. This B, it doesn't have a length per se, it has a magnitude, and this magnitude is constant all the way around. So since it's constant, we can actually pull it out of the integral here because it is constant around the bounds of integration. The bounds of integration are the 2D Amperian loop. So that means if I check here, if I check here, if I check here, if I check here, everywhere around there, the magnetic field is equal, meaning it is constant. That makes sense because this equation here, if we don't change D and we don't change I, this is always a constant. So what that's telling you is the magnetic field here around the wire is the same everywhere around the wire like this. So for that reason, we can pull this out. Integral dl. Another thing I can do is check cosine theta. I just told you guys that the way I defined it, cosine theta is 0 degrees. If I defined dl to be pointing the other way, dl would be pointing this way, b would be pointing this way, the angle here would change to 180 degrees. That doesn't matter because, well, it does matter actually. Cosine starts here, it goes like this. At 0 degrees, cosine is equal to exactly 1. If we go all the way here, this is 180 degrees. Cosine is equal to -1. So depending on how you define your Amperian loop, you might have a negative sign, you might have a positive sign. For this case, it doesn't matter. Basically, what I'm saying is cosine theta, plug in 0, cosine theta equals 1. So this whole thing equals 1, and I don't have to write it here, and I've simplified the equation a little bit more. I can rewrite the rest of the stuff here, and we have this equation here. Interesting. Now take a look at this. This integral here, we have to solve it. It equals some number. Whatever number that equals, I can divide that on both sides and get an equation for B. So B is equal to mu naught I over this integral dl. The question is this integral 0? Because if it's 0, something divided by 0 gives you some crazy bullshit. So if this is 0, I cannot do this division. But if it is not 0 and it is some number, then I can do this, and this gives me an exact number for the magnitude of the magnetic field at this point. You see how I'm piecing everything together from the picture to the equation to this? Anyway, what is this? This is basically saying add up all the DLs around your Amperian loop. What does that mean? Here's the Amperian loop. I told you we have DL over here, DL over here. We basically break up the loop into all these tiny pieces, these tiny lengths, and I add them up all the way around. All the way around my entire Amperian loop. This is why I started my entire explanation with this being the Amperian loop, because instead of having bounds here, -infinity to infinity, 4 to 6, whatever, it is a different closed loop integral, Amperian loop. So what that's saying is this integral is basically saying add up all of the dLs around this entire thing and you will get the circumference of the circle. So what is the circumference of the circle? Normally you're supposed to know this. The way I remember circumference is pi r squared. Sounds like area to me. If you need the circumference, just use pi d. Pi d is the diameter. So, pi d is the diameter. So you need to do 2 pi times the radius. In this case, the radius is d. And I think this is our final answer, which, take a look. This looks exactly the same as this. So we're chilling. Ampere's law, magnetic field. Biot-Savart law, magnetic field of a wire. Thank you guys for watching. Peace out. I hope you enjoyed my magnetism revival. Peace.